Section 3.2, Graphing Linear Equations in Two Variables. We had finished up Section 3.1 there in the homework set in the 70s, looking at equations in two variables and graphing several points on each. Let's work a problem similar to that. And let's go back to this example that we used last time. Here I have a linear equation in two variables, x plus y equals 5. And let's find ourselves several points and then graph them. I'm talking about any two numbers, x and y, that add up to 5. So, how about the point 2, 3? When x is 0, y is 5. When y is 0, what do we have? X is 5. We have points like 1, 4. Last time we said 2.5, 2.5. When x is -1, y would have to be +6. And so we have several points. Let's plot those points on our coordinate plane. Again, we want to try to do this as neatly as possible. And let's go out to 6 in all directions. The last problem in the homework from 3.1 asked if you noticed any pattern. Did you notice any pattern when it came to graphing these linear equations in two variables? And so we're going to look at the same thing here. My x-axis is a little off. I think we'll be all right this time, though. Like I say, if you want a pretty picture, look in the book, because the whiteboard does make it a little tough. We have the point 2, 3. We have the point 0, 5. No motion in the x direction, up to 5 on my y-axis. The point 5, 0, here at 5 on the x-axis, with no motion up or down. The point 1, 4. 2.5, 2.5. About right there. -1, +6, here in the second quadrant. And if we have a nice, neat graph, what we should notice is that all of these points lie on the same straight line. In fact, here at the beginning of the section, page 212, toward the bottom, the brown box tells me that the graph of a linear equation in two variables is a straight line. That is, if I were to continue plotting points, I would end up filling in a solid straight line. You might want to take a ruler and put it here for your straight edge. I'm just going to try to wing it. Every point on this line is a solution to that equation. Every solution to that equation is a point on that straight line. Now, notice the arrows on the ends indicating that it goes on forever in both directions. I insist that you put those arrows on the ends. Without the arrows, it's a line segment. It does not continue forever, and I'll have to take partial credit if the arrows are not on the ends of your graph of a line. A couple points of interest. Where this line crosses the y-axis is called the y-intercept. Where the line crosses the x-axis is the x-intercept. Those are handy points. when I go to graph a line. Your y-intercept will always be a point where x is 0. To be on the y-axis, the point must have an x-coordinate of 0. And your x-intercept will always have a y value of 0. When y is 0, you are on the x-axis. In the text, she talks about finding intercepts on page 214. Page 214 in the blue box, it says to find the x-intercept, let y equal 0. That's what happened right here for our problem. When y was 0, we found the x-intercept. And to find the y-intercept, let x equal 0. And that's what happened right there. So there will be problems in which we're simply asked to identify the intercepts of the graph without actually graphing. Let's turn to the homework set and just look at number 8 with me. Look at number 8 here in the homework. It says, identify the intercepts of each graph. And she guarantees that any point that is shown with a dot, that those points have integer coordinates. So number 8, my x-intercept where this line crosses the x-axis, that looks like it's at 4 on the x-axis. So my x-intercept, now pay attention to this. My x-intercept is the point 4, 0. An intercept is a point. It's not just a number. So, on a quiz or a test, when I ask you for the intercept, you give me a point. If all you tell me is the x-intercept is 4, it's going to cost you points, because 4 is just a number. It's not a point, so it's not an intercept. Now next semester, in Math 124, Math 126, you will probably relax that definition. And it'll be okay to say the x-intercept is 4. But right now, I want you getting used to the rigor of mathematics and the definitions and the precision. And so, at least for this semester, I'm going to insist that because the intercept is a point, when I ask you what is the intercept, you must indicate that intercept by giving me an ordered pair, giving me the full point. And what is the y-intercept here in number 8? That's up at 3 on the y-axis. So my y-intercept is the point 0, 3. Again, if you just tell me the y-intercept is 3, I have to take partial credit because 3 is a number, not a point. Let's look at number 14. We're going to slowly work our way into graphing these lines. In number 14, she is going to hold your hand as we graph this line. The instructions for number 14. Complete the given ordered pair solutions for each equation. Then graph each equation by plotting the points and drawing the line through them. I'm going to make a table instead of listing them out as ordered pairs. She wants to know when x is 0, what's y? When x is 4, what is y? And when x is negative 4. When x is 0, now that's easy. When x is 0, that term disappears, and we have what? Y equals 2. When x is 0, y is 2. When x is 4, you should be able to do that one in your head. If we're a little uncertain, it's always better to write it out. But when x is 4, we've got nice cross-canceling going. What happens? This 4 that we plugged in is over 1, so those 4's cross-cancel, to leave me negative 3 plus 2 is negative 1. So when x is positive 4, y is negative 1. And when x is negative 4, do this one in your head with me. Plug in negative 4 for x. A negative times a negative is positive. The 4's cancel to leave positive 3 plus 2 is 5. Again, it is always better, if you're the least bit unsure, to go ahead and plug in where you can see what's going on. So that negative 4 is over 1. My 4's cross cancel. A negative times a negative is positive, leaving me a positive 3 over 1, which is just 3. We found the 3 points that she asked for. Now let's graph them. Trying again to be as neat as possible. Let's go out to 5 in all directions. And we're told to plot these points and then draw the line that goes through them. The point 0, 2. No motion in the x direction, up to 2 on the y-axis. That's our y-intercept. The point 4, negative 1. Over to 4, down on the y-axis to 1, here in the 4th quadrant. And the point negative 4, positive 5. Back to negative 4 in the x direction, up to positive 5, there in the 2nd quadrant. If I've got a nice, neat graph, then I should find that all those points lie along the same straight line. And we graph this equation then by drawing the line that goes through those points. Again, I encourage you to use a ruler when you go to draw that line. And you're welcome to bring a straight edge to the quizzes and tests. You could use the side of your student ID or a sheet of paper folded over a few times as a straight edge. Doesn't have to be a ruler. Every point on this line is a solution to that equation. Every solution to that equation is a point on this line. This line represents all infinitely many solutions that there are to the given equation, this linear equation in 2 variables. Let's look at number 20. The instructions simply say, find the x and y intercepts of each graph, of each equation. We're not asked to actually graph the equation. We simply want to know what are the intercepts. Well, we find the x-intercept by letting y equal 0. And we find the y-intercept by letting x be 0. Because I know that a point on the x-axis will have a y-coordinate of 0. A point on the y-axis will have an x-coordinate of 0. And this goes back to our blue box on page 214, where she describes how to find these intercepts. So when y is 0, we plug 0 in for y. This term disappears. We have negative 3x equals 12. If negative 3x equals 12, then x must have been negative 4. We plug 0 in for x to find our y-intercept. Plug 0 in for x. This term disappears, leaving 2y equals 12. If 2y equals 12, then y must have been 6. To write the answer, now I want these labeled. The x-intercept is the point. Remember, not just the number, but the ordered pair, the point negative 4, 0. And the y-intercept is the point 0, 6. So that's what we're after. I need those ordered pairs. Number 22. We'll find our x-intercept by letting y be 0. Find our y-intercept by letting x be 0. I plug in 0 for y. When I plug 0 in for y, this term disappears. I have 3x equals 0. No mystery there. If 3x equals 0, divide both sides by 3. X had to be 0, right? 3 times what is 0? Well, that's the origin, the point 0, 0. And when I find my y-intercept, letting x equals 0, this term disappears. And that's very straightforward. Y equals 0. So this line passes through the origin. This line passes through the origin, and the x and y intercepts are both the same point, the point 0, 0. This will happen, in fact, anytime your numeric term is 0. Or, if I were to solve this for y, I could write this as y equals negative 3x. That would be the same problem. That's the same. That's an equivalent equation, has the same solution set, so it will have the same graph. If your numeric term is 0, or in other words, your numeric term isn't visible, if it's written like this, your line will pass through the origin. Look on page 217. Page 217 at the top. Line through the origin, it says, the graph of a linear equation of the form ax plus by equals 0, right there, where a and b are non-zero real numbers, passes through the origin. So if your numeric term is 0, it will pass through the origin. Let's look at number 30. Is this a linear equation in two variables? Like we said last time, yes it is. It's just that the coefficient on y must be 0. I mentioned last time that I really like to see these when there's just one variable present. I like to go ahead and solve these for the variable that is there. Add 5 to both sides. This says x is 5. And we've been asked to find the intercepts. We find the x-intercept by letting y equal 0. We find the y-intercept by letting x equal 0. Alright, to find my x-intercept, plug 0 in for y. There's no place to plug it in. That's fine. What does my equation say? It says I don't care what y is. X is 5. So the x-intercept of this graph would be the point 5, 0. Now to find the y-intercept, plug 0 in for x. You can do it in either form of this equation. I still like having it solved for x. Plug 0 in for x. What's that going to give you? 0 equals 5. That's false. No solution. So there is no y-intercept. There is no y-intercept. This should not surprise you, having done the homework from section 3.1, because if I were to graph this, which we were not asked to do, but just to quickly show, get some other points that are on this graph. What about when y is 1? Well, x is 5. When y is 2, x is still 5. I don't care what y is, x is going to be 5. The point 50, the point 51, the point 52. What kind of line is this? This is a vertical line that has its x-intercept at the point 50, and what? It runs parallel to the y-axis. And so it can have no y-intercept since it will never cross the y-axis. So the math makes sense. Now, in answer to her question, what are the intercepts? We're going to say that the x-intercept is the point 50. The y-intercept, there is none. Please don't make up your own word for this answer. Do not put undefined. Do not put no solution. Do not make up something. The x-intercept, there is none. The y-intercept. The y-intercept, what's the y-intercept? This one has none. And leave it at that. Number 36. In number 36, we're asked to graph each linear equation. Now, back in number 14, she held our hand. She said, complete these 3 ordered pairs, and then graph the line. Here, we're given the equation, and all we're told to do is graph. So what are we going to do? Well, we need to find some points on this line. Now, let me ask you this. How many points does it take to uniquely determine a line? How many lines are in the plane of this whiteboard that pass through this single point? Infinitely many. Infinitely many lines pass through that single point. How many lines in the plane of this whiteboard pass through that pair of points? Just that one. That's the only line that contains both of those points. So how many points does it take to uniquely determine a line? 2 points. Some of us, somewhere in the back of our head, seem to be remembering having been told that we need 3 points. Well, either you were told wrong, or what you're remembering is someone told you you can pick a third point to check. Pick a third point, and it should also be on that same line. So we quite often pick a third point to check our work. But we only need 2 points to actually draw the graph. Well, what 2 points should we use? There are infinitely many solutions to this equation in 2 variables. Infinitely many. We have infinitely many points to choose from. So there should be no problem coming up with a couple of points. Now, frankly, I like to use the intercepts because it lets me plug in 0. I'll find my x-intercept letting y equal 0. When y is 0, this term disappears, and we have negative 3x equals negative 6. That means x must be positive 2. I'll find my y-intercept by letting x equal 0. When x is 0, this term disappears, and we have y equals negative 6. We have enough information now to graph this line. On the y-axis, we need to go down at least as far as negative 6. On the x-axis, we'll take this out. Well, I'll stop at 4 there. Plot our points. The point 2, 0, here at 2 on the x-axis. The point 0, negative 6, down here at negative 6 on the y-axis. I have my 2 points. Lay your ruler down and draw that line through those 2 points. Don't forget your arrows on the end. We can pick a third point in order to check our work. Let's say when x is 1. When x is 1, what's that going to give me? Negative 3 times 1 plus y equals negative 6. Add 3 to both sides, and y equals negative 3. So we have a checkpoint at 1, negative 3. Where is that on my coordinate plane? The point 1, negative 3. Yep, right there on my line. And so that checks. But I really only need 2 points to be able to graph that line. Let's have a look at number 48. We want to graph this line. No one's holding our hands, so we have to come up with our own points, but that's okay. There are an infinite number of points to choose from. You pick an x and find a y, or you pick a y and find an x. I like finding those intercepts. Do you already see what's going to happen when I go to find my intercepts? My numeric term here is 0. So when I find my x-intercept by letting y equal 0, x is 0. This passes through the origin, meaning that if I go to find my y-intercept by letting x equal 0, well, y is going to be 0. So it gives me the same point. Finding my two intercepts, it turns out they're both at the same point. So right now I only have 1 point. I only have 1 point to draw this graph. Fortunately, there are an infinite number of points. Pick something. Pick some number for x and solve for y. Or pick some number for y and solve for x. We could all pick a different number for whichever variable, and we all end up with the same graph. I'm going to pick something that I think is going to be convenient, that's going to be fairly easy to deal with. I'm going to plug 1 in for x. Consider, if I plugged 1 in for y, I'd end up with a fraction for x. Think about that. If I were to plug 1 or 2 in for y, I'd end up with a fraction for x. So I'm looking at this and I'm thinking, what would be convenient? Well, plugging 1 in for x, I think, is going to be about as slick as it gets here. That gives me y plus 3 equals 0, or y equals negative 3. We have 2 points. We can graph this line. I'll go out to 3 in all directions. Not my neatest labeling of the axes, but I think it'll get the job done this time. We have a point at the origin, 0, 0. We have the point 1, negative 3, over to 1, and down to negative 3 here in the 4th quadrant. There's my 2 points. Draw the line through them. Don't forget your arrows on the ends. Any point that you would have picked, if you did the math correctly, would have landed on that same line. We'd all have the same graph. What if you had plugged in 1 for y? Well, it would have been a little messy. Subtract 1 from both sides. Divide both sides by 3. Really, it's not that bad. It's still not as slick as plugging 1 in for x, but it's not that bad. And you would have graphed the point negative 1/3, back up a little on your y-axis, and up to 1 on the y-axis, and you would have had this point right here. We all will end up with the same graph. We have infinitely many ordered pairs to choose from. But I like to try to pick ones that are convenient. That's usually the 2 intercepts. let x equal 0, and then go back and let y equal 0. But in this case, our line passed through the origin, so I had to do something else. And I picked something to plug in that I thought would be rather quick and easy. Let's do number 52. Number 52. Get a handle on these problems quickly. I said it in the last section. I'm going to say it again. We can think of this as an equation in two variables. It's just that the coefficient on x is 0, so we don't see the x. These are some of the easiest problems you can work. But it has been my experience that these are the problems on which students lose a lot of points because they don't bother to get it in their head how these work. This is so simple. Graph this line. Let's pick some points. How about when x is 0? When x is 0, what is y? Y is 3. How about when y is 0? Well, that doesn't work. Plug in 0 for y, you have a false statement. So what else can we do? When x is 1, what's y? Y is 3. What about when x is 2? Y is 3. I don't care what x is. Anything I plug in for x, y is going to be 3. What kind of line am I looking at then? The point 0, 3, the point 1, 3, the point 2, 3. You can see that this is going to be a horizontal line that passes through 3 on the y-axis. Watch this. This is the horizontal line that passes through, right here. 3 on the, right there, y-axis. The horizontal line that passes through 3 on the y-axis. So straightforward. Notice here on page 217 at the bottom. Page 217 at the bottom. Our brown box. It says the graph of y equals b, where b is a real number. In our problem, b was 3. Is a horizontal line with a y-intercept at, right here, 0b. Our number was 3. And no x-intercept, unless, of course, we're talking about the horizontal line that's on the x-axis itself. That would be y equals 0. It goes on to say that the graph of x equals a, where a is a real number, is the vertical line with x-intercept a0. In other words, it would be the vertical line that passed through that number a on the x-axis. So I want you to try the next one without me. Number 54. I want you to do number 4. Graph the equation x equals -1. Considering that that is an equation in two variables, graph that line. Go ahead and pause, and then come back and we'll compare answers. This says x is -1. Now, if we've got this down pat, and we understood that brown box, that simply means that this is going to be the vertical line that passes through -1 on the x-axis. And I'm done. If I need to be reminded, if I get stuck, I can always say, okay, x is -1. No matter what y is, x is going to be -1. And plot me some points. And that will remind me that this is the vertical line that passes through -1 on the x-axis. These are so easy, so straightforward. But students lose a ton of points on these because they don't take the time to understand them. So I strongly encourage you to get these horizontal and vertical lines down. Easy points to earn, easy points to lose. I'll leave it at that and let you get on to the homework.